Hello everyone. Today I'll be presenting quicksort, one of the most powerful and widely used sorting algorithms in computer science. If sorting were Avengers, quicksort is basically Iron Man, fast, smart, and occasionally chaotic. Quicksort uses the classic divide and conquer strategy. We take a big messy problem, like an unsorted array, and keep breaking it down into smaller, manageable pieces, solve them, and combine everything back together. Basically the same strategy we all use while pretending we are productive. Quicksort is popular because it's very fast in real-world scenarios. Even when handling large data sets, it tends to perform extremely well because it's smart partitioning. The partition is the most important part of quicksort. Hence, we can see in the pseudocode that there is a function called quicksort and there is a function called partition. The partition will be splitting the array into equal parts or usually into more or less the same type of parts. I'm talking about the average case here. And then we'll be applying the recursive quicksort algorithm back again into the same quicksort algorithm. You'll find quicksort used everywhere in libraries, frameworks, databases, and systems that need fast sorting. It's one of the go-to choices thanks to its solid performance repeatedly. We are usually using it for its average case and the best case, whereas the worst case is frowned upon in computer technology. As we can see here, we determine pivot, then start pointers from left and right. We split the array around the pivot, then recursively apply again and again in the same left and right parts of the array, unsorted array. And slowly but surely, quicksort will be sorting out the array around the pivot, then combining back into a completely sorted array. As we can see here, from step 1 to step 3, we can see that there is a pivot that is 5. And from the step 4 to step 6, we can see that the pointers are moving from left to right and right to left. There are two pointers and they'll be moving in opposite directions. When they meet, they will know that it is at the pivot element. And we can see at the step 6 and 7 and 8 that gradually the sorted array is making up itself. Quicksort pseudocode, and that's the pseudocode we have already gone through, which keeps dividing the array recursively. There will be a partition. The real hero that rearranges the elements around the pivot. The pivot is like a bouncer standing in the club doorway. Every element smaller than the pivot will be going to the back door, and the bigger ones go in. Uh, Quicksort. The full source code can be viewed on GitHub. I'll be linking it in both the description and in the PPT itself. In e-commerce, in e-commerce search results, we usually look at sort by, filter by, etc., etc. It's widely used. Quicksort quickly sorts the array as the name suggests, obviously. Quicksort finds real-world application in e-commerce, in many websites, Amazon, Flipkart, Myntra, etc., etc. There's a lot of applications to quicksort. Whenever we sort by price, popularity, or the discounts or the sales, the algorithm runs itself over all the large database. It quickly sorts all of it and shows us the result as to our liking. We have already linked the code to an e-commerce. It's not as complex as one might think an e-commerce website looks. It's something that's more or less the same thing. It roughly gives you an idea about what it is and how it might look. And coming to the recurrence relation analysis, we can look at the recurrence relation. It will be splitting the array, taking a pivot. So usually, as you can see that it will be splitting it into more or less the same half, half, so n by 2. And in each side of the array, we'll be running it again and again. So for every step, there is 2 times itself. As you can see here, 2 into t of n by 2 plus n. Using master theorem, uh, and here we can look at that from the basic relation of master theorem, a of a into t of n by b plus f of n. Here the f of n will be n, a is 2, b is 2. And from the first case on the first relation of master theorem, we can conclude that the time complexity of quicksort will be theta of n log n. The best case occurs when the pivot consistently divides the array into rough equal halves. So more or less it should be more unsorted so that it can run a lot quicker. And the worst case occurring when the pivot is highly unbalanced. And this is the case where the array is already sorted, which is the worst case for a quicksort, where we'll be looking at other sorting algorithms. I'm sure you know of it. Excuse me. And finally, the time and space complexities. To summarize, the best case will be O of n log n. The average case will be same O of n log n. The worst case O of n square. As I said, the already sorted array will be taking its pivots very bad. So quicksort is usually preferred for great average performance, minimal extra memory. The in-place sorting will be allowing us to sort the array without the extra memory we'll be needing to put in case of other sorting arrays. I mean sorting techniques. And yeah, that's basically it. Quicksort is really simple to understand. There is a partition and there is a quicksort. Wherever there is a partition, the left and right halves will already put it again recursively. That's basically all of it. It's used for its average time complexity. It's bad when it's already sorted, as I said. And it is great for in-place sorting, so that wherever there is a case of we can't see, for an example, if we look at a case that I can't afford extra memory, but I need the things to be sorted. I'm willing to give up some sort of performance. I will be going for quicksort. Quicksort is highly sought after in web applications, the sorting techniques, and e-commerce, as we linked before. So yeah, any sort of questions are completely fine. Hoping that they're easy, and hope that you completely understood about quicksort. And you can kindly check after the links in the description and the PPT. My GitHub ID is also linked in the description, so kindly be off there. Thank you.